Okay, so in today's lecture, we'll be discussing chapter 3, which focuses primarily on nomenclature, which is naming compounds and writing the formulas of compounds given the name. So let's do some quick review into writing the formulas of elements. So the periodic table can be divided into three major categories of elements: your metals, your nonmetals, and your metalloids. Now, this is important because depending on whether your element is a metal, nonmetal, or a metalloid, it in turn will have different rules for predicting the chemical formula for that element. So for example, your atomic elements, which consist of a single atom, are made up of your metals and your noble gases, where your noble gases are your group 8A elements. So would someone like to give me an example of a metal? What's an example of a metal if we were trying to write the formula? Let's just get an example of a metal in the chat. Sure, iron. So iron would be written as Fe solid, where we only have one atom in the chemical formula for this pure element. Let's try to get an example now of a noble gas. What is an example of a noble gas if we wanted to write the formula for a noble gas? Helium, sure. So helium would be written as helium gas, where we just have one atom of helium in our chemical formula. Does this make sense so far? Now, for your molecular elements, these are your nonmetals and your metalloids. And the molecular elements are divided into two subcategories. Your diatomic elements, which are comprised of two atoms. These are your halogens, oxygen, nitrogen, and hydrogen. Would someone like to give us an example of a halogen? What is the typical formula? What is an example of a halogen for us to write the formula for? Sure, chlorine. So chlorine would be written as Cl2 gas. We have two atoms of chlorine in our chemical formula. So just to give an example, one of these other compounds on the list, one of these other elements on the list, hydrogen would have a formula of H2 gas. We have two atoms of hydrogen in our chemical formula. It's a diatomic element. Now our polyatomic elements are comprised of three or more atoms, and these are primarily sulfur and phosphorus, where sulfur is S8 and phosphorus is P4. This is review from chapter 1 of the notes. Any questions on writing the formulas of elements from their name? If not, let's continue our discussion and let's talk a little bit about the physical states of elements. Let's talk a little bit about the physical states of elements. So, the state symbol indicates the physical state of each substance. So S for solid, L for liquid, G for gas, and AQ for aqueous. So aqueous essentially just means it's dissolved in water. Now, in order to have a complete formula that really gives you the full context, it's important to be able to write the state symbol whenever possible. So, metals are solids at room temperature, and these include sodium, aluminum, and zinc. As one exception, mercury is a liquid. Now, for your nonmetals, it gets a little bit more involved. So for your nonmetals, your noble gases, and then hydrogen, nitrogen, oxygen, fluorine, and chlorine are gases. So they get a G symbol. So for example, for another noble gas, we'd have argon, and argon would get a gas symbol. If we were writing out a complete formula for hydrogen, we'd put a gas symbol to indicate that hydrogen is a gas at room temperature. For nonmetals, only one of the major nonmetals is a liquid at room temperature, and that's bromine. So bromine would be written as Br2 liquid. And as a rule of thumb, most other nonmetal and metalloid elements are solids. So for example, iodine would get a solid symbol. Now there's a special term that we need to talk about with regards to two formulas for an element in the same physical state. We call these allotropes. They're multiple distinct chemical formulas of an element in the same physical state. So for example, oxygen has the formula of O2 gas. An allotrope of oxygen, which is ozone, has the formula O3 gas. Both of these samples represent the element oxygen. However, these two samples of oxygen each have a different number of oxygen atoms in their formula and the same physical state. Usually, and overwhelmingly, an allotrope will have a specific name associated with that allotrope in order to allow you to write the chemical formula for that allotrope more readily. Does this make sense to everyone so far? Any questions so far? If not, let's keep going then. So looking at ionic and covalent compounds, again, a little bit more review. So our goal is to be able to classify compounds as ionic or covalent compounds. This is critically important in order to effectively name these compounds. So a compound is a substance containing two or more different elements. Compounds can be either ionic or covalent. So for our ionic compounds are composed of a positively charged cation and a negatively charged anion. Now, overwhelmingly, for ionic compounds, you're typically going to see a metal cation and a non-metal anion. So just to give you an example of that kind of formula, we could have, for example, sodium fluoride, where sodium is our metal cation and fluorine is our non-metal anion. And one thing to note is that this ratio doesn't need to be 1-to-1. You can have compounds like, for example, lithium phosphide, in which there is an unequal number of cations and anions. And that's because the cation and anion have a different charge. Okay. Now, there's another subclass of ion that we need to talk about, and that is the polyatomic ion. A polyatomic ion is a charged molecule containing two or more atoms covalently bonded. So there are many examples of polyatomic ions. They can be both collections of atoms of the same element or different elements. So for example, one polyatomic ion that we'll see later on this class is I3-. Another example, more on the compound side of the spectrum, would be something like carbonate, where we have CO3 2-. In both cases, we have a molecule with a net overall charge. Now we've so far drawn anionic species, but we can certainly draw a cationic species, such as ammonium plus. So in this case, this is a cation. Well, our previous two examples were describing anions. Now, when we're talking a little bit about ionic compounds, we often use the term formula unit, which is the smallest repeating set of ions in an ionic compound. I like to think about the formula unit when someone mentions the idea of formula units. I like to think of it as molecules of your ionic compound. It's not a perfect definition, but it really catches the majority of the cases where you'll see formula units mentioned in the early parts of this class. We'll come back to formula units in later chapters once we have a better sense of how we want to begin to describe solid materials and arrangements of ions in ionic compounds. So an example of a formula unit, so if sodium oxide has the formula Na2O, the simplest formula unit, the simplest repeating unit of ions would consist of 2 sodium ions and 1 oxide ion. And we'll talk about how we're determining these charges momentarily. Now, the next major subclass of compound is the covalent and molecular compound. So we have 2 or more atoms. This time, again, as it's a compound, there are different elements. And for covalent and molecular compounds, they are covalently bonded together. Covalent and molecular compounds are overwhelmingly comprised of 2 or more nonmetals, and they're neutral with no charged ions. So an example of a covalent and molecular compound, water is a good typical example. Other examples include carbon monoxide and methane. In all of these examples, we have 2 or more nonmetals, and each of the components of this compound are neutral. There's no charged ion present in any of these compounds. Does this make sense so far to everyone? Any questions so far? If not, let's continue on. So, a key factor in terms of understanding the nature of a chemical bond and predicting whether a compound is ionic. So yes, we will be discussing polyatomic ions momentarily, and you will have to be familiar with all of the polyatomic ion names and formulas, yes. So returning to this idea, so a central feature that helps us predict whether a bond, and by extension whether a compound is ionic or covalent, is by looking at the sharing of electrons in chemical bonds. And the electronegativity of atoms in our chemical bond directly influences the nature of our chemical bond. So an ionic bond is an electrostatic interaction between a cation and an anion. So there's no sharing of electrons. Quite simply, it's just an attraction between charged particles. So we know from our previous lecture that charged particles of opposite charge attract. Coulomb's law in action. Now, ionic compounds are composed of a cation and an anion. And to talk a little bit about how we actually form an ionic bond are formed from neutral elements via the transfer of electrons from one element to another. So there's not a sharing of electrons. It's more as if one element gives electrons, loses electrons, the other element takes electrons or gains electrons. So in this case, if we had to think about this for copper bromide, we'd have initially our copper atom and our two bromine atoms. And when they want to form a bonding interaction, copper will donate 1 electron to each bromine atom. That in turn gives us a set of charged ions. And because those ions have an opposite charge, they will experience a very stabilizing electrostatic and attractive interaction. Okay, so the key feature that I want you to take away from this idea of ionic compounds is there's no sharing of electrons. It's a strict transfer of electrons, and an ionic bond is an electrostatic interaction. It's an attraction between particles with opposite charges. So, continuing on with this idea, a covalent bond involves the sharing of outermost electrons between two atoms. So in this case, rather than a transfer of electrons, in a covalent bond, there's an explicit sharing of electrons. So for example, if we have two hydrogen atoms participating in a covalent bond, these hydrogen atoms will share electrons, and these shared electrons are often depicted with a dot or a line. And these shared electrons represent what is known as a covalent bond. Now, of course, atoms can share more than just one pair of electrons. And from this, you can get relatively interesting bonding arrangements and structures. But the key feature of covalent compounds that I want you to take away from this is that there is a sharing of electrons between atoms. Any questions so far? Any questions so far?
For the top one, for the ionic bond, is that second drawing before it shares or after it shares?
The second drawing is so after it transfers electrons, yes. So these are the ions that you'd see in your ionic compound, and essentially these ions experience an attractive, stabilizing interaction that we call an ionic bond. Does that make sense?
Yeah.
Perfect. So then let's talk a little bit about a tool that we have available to begin to predict the nature of a chemical bond. And it concerns this idea of electronegativity. So the following is the electronegativity scale. And one thing that we want to note really quickly is I like to draw an arrow going up and to the right. This arrow indicates increasing electronegativity. So just graphically, we can conclude as we go to the right and up the periodic table towards fluorine, the electronegativity of our elements increases. Now, what is electronegativity? So electronegativity is how readily a nucleus attracts electron density in a chemical bond. How readily does an atom pull electron density in a chemical bond? So, for example, if we have something like sodium fluoride, sodium is not very electronegative. So sodium is not very electronegative, as we can see by its value of about 0.9. While fluorine is very electronegative. So if we think about what would happen if we have some electrons and we try to share electrons between sodium and fluorine, fluorine would pull on these electrons in a very strong manner. It really wants to draw electron density towards itself, and it really wants to gain electron density because fluorine is more electronegative, and fluorine is very electronegative. What results is, depending on the difference in electronegativity between your atoms, you may either see an ionic or covalent compound. In this case, we get an ionic compound as the fluorine takes the electrons from the less electronegative sodium. So I like to think about electronegativity in terms of this idea of how strongly does our atom pull electron density towards itself in a chemical bond. Now, most of our electronegative elements, as we can see, are on the right-hand side of the periodic table. What elements are on the right-hand side of the periodic table? Are those the metals or non-metals? So if you look at this electronegativity table, what elements are on the right-hand side of the periodic table for the most part? Yep, the non-metals. Okay, and what elements are on the left-hand side of the periodic table? What elements are found on the left-hand side of the periodic table? The metals. And the metals are not particularly electronegative. They have relatively low electronegativity values. So one thing that we can conclude from this, and one general trend that we observe, is that electronegative elements, such as our nonmetals, prefer to form anions. So that's why we get anions like chloride, fluoride, oxide, and phosphide. All of your nonmetals, which are very electronegative, prefer to draw electron density towards themselves in a chemical bond to such an extent that they actually end up taking the shared electrons in a chemical bond, and you end up with ions. So less electronegative elements, such as metals, prefer to form cations. So for example, your sodium goes to sodium plus, calcium goes to calcium 2 plus, aluminum goes to aluminum 3 plus. Okay, so we have sort of a correlation beginning to develop between electronegativity and ion preferences. Let's keep going now, and we'll discuss this idea of the chemical bonding continuum. So depending on the delta En, which is known as the difference in electronegativity between two atoms in a bond, we will have different types of ionic and covalent bonds. So there are three major categories of chemical bonds to look at, each with different differences in electronegativity. The first is our ionic bond, followed by the polar covalent and the pure covalent. So the pure covalent, that we call a non-polar bond, has a difference in electronegativity of less than 0.4. This primarily occurs when you have, for example, CH bonds or atoms containing two elements with a very small difference in electronegativity, or essentially an XX bond, where you have two atoms of the same element chemically bonded to each other. So this idea of delta En, it's not the absolute electronegativity, it's the difference in electronegativity. So for example, if you have a chlorine-chlorine bond, both of these atoms have an electronegativity value. And if we go to our chart just to get an accurate value, you're not expected to memorize any of these. Both of these chlorine atoms have an electronegativity value of about 2.7. And since they're the same element, our difference in electronegativity is equal to 0. So between our two chlorine atoms, we have an even sharing of electrons. So this is as pure of a covalent bond as you can get. There's a straight even sharing of electrons between your atoms in this chemical bond. In the case of CH bonds, the difference in electronegativity is about 0.1. So even though there is a slight difference in how readily both of these atoms pull electron density towards themselves, it's so small that we have functionally an even sharing of electrons. Okay. The next major type of covalent bond is known as a polar covalent bond. And this occurs when we have a difference in electronegativity of greater than 0.4 and less than 2.0. So an example of a polar covalent bond would be, for example, HCl, where chlorine has an electronegativity value of 2.7, hydrogen has a value of about 2.1. That gives us a difference in electronegativity of about 0.6. Now, what this is telling us is that if we look at a hydrogen-chlorine bond, which of these two atoms is pulling electron density more strongly? Which of these two atoms is more electronegative? Chlorine, yeah. So our electron density in our chemical bond is being pulled towards chlorine. And as a result, we can think of it like more of our electron density is on chlorine than on hydrogen. Now, because we have excess electron density on chlorine, what do we call a charged species with excess electrons? What kind of charge will we accumulate if we have excess electrons on our chlorine atom? What kind of charge will we accumulate? Positive or negative? Negative, exactly. So we don't generate a full charge, but we generate what's known as a partial charge. So this delta is signifying a partial charge because the chlorine has a little bit more electron density than usual. What about hydrogen? What about hydrogen? Does it have more or less electron density than usual? Is hydrogen electron rich or electron deficient in this compound? It has less, yeah. So it has less electron density because chlorine is pulling away some of the electron density that's supposed to be on hydrogen. So that in turn gives us a delta plus partial charge. So we can represent this idea where we have a separation of charge, and we call this separation of charge a dipole. And we draw our dipole as an arrow starting from our partially positive element, typically our least electronegative element, and pointing towards the region with the most electron density, with the partial negative charge, or the most electronegative element. So as we can see, when there's a difference in electronegativity, we end up with an uneven sharing of electrons. So in a polar covalent bond, I'd like you to think of it as the idea of uneven sharing of electrons. This uneven sharing of electrons results in excess electron density on our more electronegative element, which results in the buildup of a partial negative charge. The less electronegative element such as hydrogen, has electron density pulled away from it. And as a result, it accumulates a partial positive charge. This separation of charge is represented by a dipole, which we indicate by drawing an arrow from our partial positive atom to our partial negative atom in our chemical bond. Does this make sense to everyone so far? Does this make sense to everyone so far? Any questions so far? If not, let's talk about our final class of compound, and it occurs when we have a difference in electronegativity of greater than 2.0, and this is our ionic bond. So let's look at an example of sodium fluoride. So fluorine has an electronegativity value of 4.0. Sodium has a value of about 0.9. Our difference in electronegativity is about 3.1. So what this is saying essentially is that if we had electrons between sodium and fluorine, fluorine is so strongly electronegative and sodium is so weakly electronegative that fluorine, instead of sharing the electrons in an ionic compound, the fluorine takes electrons from sodium. Another way you can think about it is that sodium donates electrons to fluorine. So these electrons are no longer shared, they're just transferred to fluorine. And that in turn gives us a set of ions, and these two ions will attract each other, and this attractive interaction forms the backbone of our ionic compound. So essentially, the greater the difference in electronegativity, the more one of your elements is pulling electron density towards itself. However, if your difference in electronegativity becomes too large, then one of your atoms, instead of unevenly sharing electrons, one of your atoms will just take electrons from the other atom. And this results in an ionic compound. Does this idea make sense so far to everyone? Any questions so far? If not, let's continue on and let's talk about periodic trends and ions. So, we've seen from our previous discussion that metals aren't very electronegative. So in chemical bonds, metals will typically lose electrons. And when they lose electrons, they will form cations. More specifically, however, for main group metals, which are A group metals, they tend to form cations with charge equal to their group number. So again, groups have a lot of power in terms of sorting elements via reactivity, and we'll see that come in full force in this next section. So for example, if we have magnesium, which is a group 2A element, what ion would we expect to generate from magnesium? What's the charge of our ion that we would expect to generate from magnesium following this rule? What's the charge going to be? +1, +2, -1, -2. What is the group number of magnesium? And don't be shy to respond via the chat. What's the group number of magnesium? Well, the group number of magnesium is 2A. So we'd form a cation with charge +2. Let's do another example. What about lithium, which is a 1A element? What charge would we expect to see for lithium based on that reasoning? +1, exactly. So we'd expect lithium to generate lithium plus. Perfect. So for our nonmetals are pretty electronegative, and as a result, they typically gain electrons. As these nonmetals gain electrons, they prefer to form anions. So as a general rule, nonmetals like to form anions with charge equal to the group number -8. And when we talk about electronic structure, we'll be able to fully rationalize this rule utilizing electron filling diagrams. So oxygen is a 6A element. So then 6 minus 8 gives us -2. So we predict that oxygen would prefer to adopt a 2- charge. Would someone like to propose the charge for nitrogen in an ionic compound? What charge would nitrogen prefer to adopt in an ionic compound? Yep, 3-, exactly right. 5 minus 8 gives us -3, so this would be nitrogen 3-. Perfect. Now, it's important that you don't get too overzealous and try to apply these rules to transition metals. Transition metals, or B group metals, typically adopt a +2 charge, but they can adopt a range of positive charges. So for example, copper can be anywhere from copper+ to copper 2+ to copper 3+. So you can't just predict the charge of a transition metal from the periodic table. It depends on what compound the transition metal is a part of, among other factors. However, there are some transition metals that follow predictable charge rules. These are your fixed charge transition metals, which you'll have to memorize. Silver, cadmium, and zinc form silver+, cadmium 2+, and zinc+. So these are the 3 transition metals with a fixed charge that you'll need to be familiar with for this class, as they do actually appear a fair amount in labs and in common chemical reactions. Does this make sense so far to everyone? Any questions so far? If not, let's keep moving on and let's try to tackle the next example. So let's do a guided example now where we have to predict the charge of each ion formed from each of the following atoms. So in this case, we have magnesium. So magnesium, looking at the periodic table, is a 2A element. So it will prefer to form magnesium 2+. Sulfur, which is a 6A element, will prefer to form sulfur 6 - 8, which is S2-. Silver is a fixed charge transition metal, so it'll prefer to form silver+. And nitrogen, being a 5A element, will prefer to form nitrogen 3- because 5 - 8 is -3. Do these examples make sense to everyone so far? So if everyone's comfortable with these examples, oh, okay, I'll give everyone a moment to continue writing. It's personal preference. It's personal preference whether you put the sign before or after the number. Any other questions I can address? So the basis behind this has to do with this idea that atoms really prefer to want to have 8 outer electrons or an octet of electrons. And this shortcut that I'm showing you to predict the charge of these common ions is based on this idea that most main group elements follow what's known as the octet rule, or the 8 outer electron rule. We'll delve more into why this rule works in later chapters once we understand electronic structure and electron configurations. Does that make sense? For now, we're sort of stuck using these charge prediction rules because this is critical to beginning to start to write out and put together the formulas for ionic compounds. Did that address your question? So you will have to know the charge preferences for your fixed charge transition metals, yes, the Zoom meetings you can leave and rejoin if there's a technical issue, and that should fix the problem. For the transition metals, you don't have to memorize all of their preferred charges, but for fixed charge transition metals, you will have to memorize their charge preferences. For the other transition metals, it varies depending on what compound that transition metal is a part of. Does that make sense? So you don't have to, quote unquote, know all the transition metals. You just have to know how to calculate their charge using some rules that I'm going to teach you later on in this chapter. So silver is a fixed charge transition metal. Oops, one moment. Let me zoom in. Sorry about that. Sometimes there's a bit of a delay over the course stream. Okay, so silver is a fixed charge transition metal. And it's found that silver prefers to form silver plus cation. It's a bit of an unsatisfying answer for now. The full reason is the fact that silver is an S1d10 metal, and so it prefers to lose 1 electron to have a full d orbital. But we need a little bit more background information before we can parse and break down why different atoms adopt a specific charge. And that will be covered in the chapter on electron configuration. This first chapter is just laying out how do I predict the charge of ions. And the reason why we need that information is because we're going to take these ion charges and we're going to put them together and we're going to use them to predict the formulas of compounds. We're going to use these ion charges also to begin to name compounds. So because we're going to be often using the names of compounds throughout this class, we want to develop that skill. And in terms of what's going on behind the scenes that makes this rule works, that requires us to talk a little bit more about chemical reactions and chemical reactivity before we can fully delve into electronic structure. Does that make sense? So the short answer, silver is a fixed charge transition metal, and it's found empirically that silver prefers to adopt a +1 charge in compounds. The longer answer, it's based on the number of electrons that silver has, and silver really would prefer to lose one and only one electron to make a stable ion. Any other questions that I can address? Any other questions that I can address? If not, let's take a moment and let's work on the following Canvas example. Allow it one moment. Let me just quickly reset OneNote, just so that way there's not as much of a delay. Okay, so let's open up Canvas quiz and problem solving session 3.5, and let's work on the following 4 problems where we try to predict the charge of each ion formed from each of the following atoms. Yep, and that's fine. So you'd put +1 or -1, +2 or -2. You just put the number and the sign, and the problem will recognize whether you've assigned the charge correctly. Does that make sense? Oh, it should be recognizing the sign. If not, just enter the magnitude and we'll talk about the sign when we discuss the solution. Oh, okay, perfect. And we'll discuss in about 3 minutes. So we already see some reasonable responses so far. I would try to identify the group number and the location of scandium in the periodic table and just double check that. Let's try to get a few more responses via. So one thing I would look at is that in general, metals adopt charge equal to their group number, and early stage transition metals, you can apply this rule to loosely. So scandium is a 3B transition metal, and from that information, you may be able to conclude something about a potential charge preference for scandium. So let's take about 2 more minutes and work through this problem, and then let's try to get a few more responses via the Canvas quiz or via the chat feature. Yep, the scandium 3+ looks reasonable based on the group number 3B as a tentative tool for assigning the charge. Yep. And we'll discuss in about another 30 seconds to a minute. Let's try to get a few more responses in the chat and via Canvas. So when you start moving deeper into the transition metals, the rules no longer easily apply. But for the early stage 3B transition metals, all the way up to the 4B transition metals, they generally prefer to adopt a charge equal to their group number. So let's look at these examples and let's talk through each of them. So bromine is a 7A element. So then 7 minus 8 gives us -1. So bromine prefers to adopt a -1 charge. Lithium, as a 1A element, adopts a charge of +1. Now zinc is a transition metal, but it's something special about zinc. Do we know the preferred charge for zinc? What charge would zinc prefer to adopt? +2. Yep, it's a fixed charge transition metal, and zinc overwhelmingly prefers to form zinc 2+. So scandium, I'm just going to put a little star next to it because your 3B transition metals are a slight exception from the rule. In general, transition metals, you just have to figure out the charge by looking at the formula for the compound that the transition metal is a part of. But for early stage, such as 3B transition metals, they overwhelmingly also adopt a charge equal to the group number. So scandium will overwhelmingly form scandium 3+. This is an exception, but it's one that I wanted us to talk about briefly, as it's relatively intuitive if you just contrast it with the main group elements. This does not apply to all transition metals. In fact, we're going to be developing rules momentarily to calculate the charge of the metal in a transition metal.
May I ask how zinc is 2+? Because isn't it in the transition metals?
Yes, but zinc is another one of our fixed charge transition metals.
Okay, it's like an exception.
Yep, and as a result, zinc will almost always form zinc 2+.
Okay, thank you.
Yep. Any other questions I can address? If not, we'll continue on and talk next about polyatomic ions. So polyatomic ions, it's a charged molecule, an ion, containing 2 or more atoms covalently bonded. So here is a list of polyatomic ions that you're responsible and you can be tested on. And you should be familiar with all of these polyatomic ions in this list. So we've sorted polyatomic ions based on their charge. And I really feel it's important when you go about memorizing the formulas of these polyatomic ions and their name, that you take a moment and really focus on making sure you know the charge, as charge is critically important in our rules for predicting the formula of ionic compounds and predicting the charge of metals and other species in our ionic compounds. So make sure you're focusing on the charge, formula, and the name. If you don't know the charge, it's very difficult to solve these kinds of problems. Okay, so before you get overwhelmed with looking at this table and thinking that's a lot to memorize, there's actually a logical pattern to organize our discussion of polyatomic ions. So the per-8 prefix, so depending on the prefix and suffix, the polyatomic ion changes. So the per-8 prefix and suffix indicates the ion with the most oxygen atoms. Another way to think about it is the per-8 ion is the ion with 1 more oxygen atom than the 8 ion. So for example, ClO4 is known as per chlorate, while ClO3 is known just as chlorate. Does everyone notice how when the prefix and suffix change, our chemical formula for our polyatomic ion changes? Now, the polyatomic ions that you're going to be memorizing, and the ones that I recommend that you start memorizing, are the 8 polyatomic ions. These are the polyatomic ions with the second most oxygen atoms. And it's easiest to memorize the 8 ion for each set of polyatomic ions. So for example, NO3 minus is nitrate. SO4 2 minus is sulfate. Notice, and this is really important, not all 8 ions have the same number of oxygen atoms, nor the same number of the same charge. So I don't want you to get the idea that, for example, 8 always means 4, because it's different for different polyatomic ions. But if you memorize the 8 ion, such as nitrate, sulfate, you can modify the name, the prefix and suffix for your 8 ion if the formula of your polyatomic ion is different. So for example, the next suffix that we often see is the "ite" suffix. It's the ion with 1 less oxygen atom than the 8 ion. So for example, NO2 minus is known as nitrite, while SO3 2 minus is known as sulfite. And a key thing that you want to pay attention to is, as we can clearly see, when using this prefix and suffix system, the charge of your polyatomic ion will remain the same. Does this make sense to everyone so far? Any questions so far? So the next prefix and suffix combination that we see is the hypoite prefix suffix combination. This is the ion with the least number of oxygen atoms, and I'm just going to put a star next to it. Among the polyatomic ions that we typically look at, this rule will work just fine. You can also think of it as the ion with 2 less oxygen atoms than the 8 ion. So what do I mean by that? So PO4, let me write it out in a different color just so that way we can contrast. So ClO4 minus is known as perchlorate. ClO3 minus is known as chlorate. ClO2 minus is chlorite. And ClO minus is known as hypochlorite. So the hypoite pairing indicates the polyatomic ion with 2 less oxygen atoms than the 8 ion. In fact, let me write it in the same color, just so that way it's easy to make that correlation. Likewise, we can look at other examples of hypoite polyatomic ions. So PO4 3 minus is known as phosphate. So then PO2 3 minus is known as hypophosphite. Does this make sense to everyone so far? Any questions so far? Okay, so serves as a framework for memorizing the polyatomic ions. If you're so inclined, you can memorize them via just brute force. Whatever works for you. You do want to be familiar with these names, however, as you really don't want to be stuck when you're staring at a problem going, what does that name mean? You want to be able to recall it quickly so that way you can focus on solving the actual problem. As chemists, we will talk about compounds using their verbal name. We won't speak and saying like ClO2 minus. That's a little bit awkward to say compared to chloride. So you have to be familiar with the names and formulas of each of these polyatomic ions so that we can use these rules to talk about compounds containing polyatomic ions. So let's do some review. So before we talk about formula prediction, let's just make sure that we know how to read a chemical formula. So this subscript indicates the number of atoms of that element. So this subscript of 3 indicates that we have 3 chlorine atoms. Subscripts can also indicate the number of polyatomic subunits or ions. So in this case, this 2, the subscript of 2, applies to everything in the parentheses. So we have a total of 3 calcium atoms and a total of 2 pairs of phosphate ions, which in turn would mean we have a total of 3 calcium atoms, 2 phosphorus atoms, and 8 oxygen atoms. So let's do a guided example. Let's indicate the atoms of each element in the following compound. So in copper cyanide, we have 1 copper atom, 3 carbon atoms, and 3 nitrogen atoms. In sodium hydrogen phosphate, we have 2 sodium atoms. We have 1 hydrogen, 1 phosphorus, and 3 oxygen atoms. So let's take a moment and let's work through this problem solving session. And I just want to put a side note here. These next problem solving sessions will be posted later today or tomorrow for you to enter the results from your notes into Canvas and for you to try to reattempt these problems if you prefer. I'll be going through and allowing all of these problem solving sessions to be open for retakes. But I just wanted to make sure the format was perfect. So we'll work on these and I'd like you to submit your responses and ask questions via the chat. We'll spend about 2 minutes on this problem. And then I want you to save your notes and then you'll have the opportunity to reattempt these problems in approximately 1 day. And I'll make sure all of these problem solving sessions are open for retakes if you want to use them as additional study tools. Does this make sense? So let's take about 2 minutes to work through this problem, and then we'll come together as a group to discuss. Yes, these haven't been opened just yet. I'm still checking to make sure that the Canvas formatting is correct and that it works reasonably well in a student view, but they'll be posted for a retry by tomorrow. But you're welcome to message me your proposed responses in the chat, either publicly or privately, and I can provide feedback at this time. So I'm already seeing some reasonable responses so far for these 2 prompts. Let's spend about another minute on this problem. I want to see a reasonable collection of responses from the students, and then we'll discuss momentarily.
I'm not sure if I just keep missing it. I can't seem to find the Canvas quiz 3.7.
Yeah, these from here on for this lecture, they haven't been posted just yet. They're
I'm sorry.
oh, no. It's just because I wanted to do a few more tests on some Canvas features to try and get these questions as close as possible. Does that make sense?
Yes, I'm so sorry.
Oh,
I know
no,
you explained that.
no problem at all. No problem at all. So let's now discuss this problem, and let's tackle this first example. This is ammonium dichromate. So first and foremost, sorry about that. There was a small delay in the Zoom stream. So first and foremost, this subscript applies to all atoms in our parentheses. So we have 2 nitrogens, 8 hydrogens, 2 chromium atoms, and 7 oxygen atoms. For magnesium phosphate, we have 3 magnesium atoms. The subscript again applies to all species in the parentheses. So 2 phosphorus atoms and 8 oxygen atoms. Any questions on this example? Any questions on this example? If not, let's continue on and let's talk about the process to predict the formulas of ionic compounds. So we're first going to start with a general rule that stable, isolable, solid ionic compounds, I know that's a lot of qualifying statements, are typically neutral with a total charge of 0. Generally, you can't have isolated charges in nature. Charges typically come paired, where you have a cationic positive charge and an anionic negative charge. So the total charge of an ionic compound is the sum of the total charge of each ion. So for your cations, we add up the charge of each cation times the number of each cation. For our anions, we add up the charge of each anion times the number of each anion. And the total charge, and this is really important for most ionic compounds, will be 0. So in order to use this equation, first things first, we need to determine the charge of each component ion. We can do this using periodic trends. Remember, looking at the group number of our element. You can also do this by recalling the common charges for your polyatomic ions. This is why I'm having you memorize the polyatomic ions and their charges. And as a third option, and we'll talk about this more when we cover transition metal nomenclature, names involving metal ions will include the metal cation charge. So for example, iron 2 bromide, this Roman number 2 indicates the charge. So let's suppose for a moment that we have a compound that contains sodium and oxygen. So let's suppose we have a compound that contains sodium and oxygen. What would we predict for the preferred charge for sodium? What would we predict for the preferred charge of sodium? What's the preferred charge of sodium, which is a 1A element? +1, yep. Okay, what about oxygen, which is a 6A element? -2, yep. Because 6 minus 8 is -2. Okay, let's make a little dividing line here and let's look at another example. This time we have barium, okay, and carbonate, which has the formula CO3, so carbonate. What is the preferred charge for barium, which is a 2A element? What is the preferred charge for barium? Yep, +2. And for carbonate, what is the preferred charge of carbonate? This one you'll need to go back to that polyatomic ion table. So for carbonate, it's actually 2-. And what I want you to do, especially in these examples, is to have the polyatomic ion table available. You can try first starting the problem with the table inaccessible to you. And then if you're stuck, you can turn it over. And really by working through problems where you're utilizing the knowledge found in this table, I found it's easier to memorize each of these polyatomic ions if you're actively using them in naming problems. So next, the rule of thumb is if the ionic compound is neutral, what you can do is you can place the charge of your ion into the subscript of your opposite ion. We call this idea crossing charges. So this would give us Na2O for sodium oxide. Now there's one little asterisk that we need to note. The ratio of ions should be the simplest whole number ratio. The simplest, smallest whole number ratio. So let's see where this rule applies when we look at barium carbonate. So we have barium 2+, CO3 2-. So now we cross our charges. And we'd initially predict a formula of barium 2 carbonate 2. Whoops, one moment.